So we're on to the last stretch that is in this first chapter. Really, it's the first chapter of the textbook, all right? For today, we're not going to talk about why they lose them easily or why they hang on to them with great force. We're just going to talk about what happens when they gain or lose electrons and the fact that they become positively or negatively charged ions. Okay, so definition of what an ion is. An ion is a charged atom formed by adding or removing electrons from the valence shell. You've heard the term valence before, all right? Valence often means outermost, the outermost shell, okay? Or sometimes they might say valence electrons. It means outermost. The electrons that are in the outermost shell, the ones that are furthest away, like we saw in our Bohr and Lewis diagrams. So let's talk about cations. And they're the positively charged ions formed by removing an electron from the valence shell. Take an electron away. It leaves an imbalance between protons and electrons. More protons than electrons. The overall charge is positive. The size of the positive charge is equal to the number of electrons which has been removed. Metal atoms tend to lose electrons to form cations. So metals have a weak hold on their electrons. Those electrons are lost for some reason, and they form cations. A stable cation is one in which all of the valence electrons have been removed. So for sodium, that would be 1. It's got 1 outer electron. If we recall our Bohr and Lewis diagrams from way back last week. Magnesium has 2. It will lose 2 to become stable. Aluminum has 3. It will lose 3 to become stable. All right? Once they've been all removed, this leaves an empty valence shell. So for these metals, we're clearing out the valence shell. For elements up to calcium, the stable cation is isoelectronic to the nearest noble gas. I will be talking a little more about that in a moment. What do you think isoelectronic means? Yep. Same electrons, right? If you take 2 electrons away from magnesium and empty that shell, then it's going to become the same as a neon, right? Because magnesium has 2, then 8, then 2. When you make the stable ion and take the 2 away, it becomes the same as neon, 2, 8. So isoelectronic means same electrons. Actually, the term we use is electron configuration, the configuration or location of the electrons. Okay? All right. A little introduction to what we're going to be talking about for the rest of the week. When you take an electron off of an atom, it requires energy. The minimum amount of energy to remove an electron from an atom is called the ionization energy. To form the ion, hence ionization, and it takes some energy. Now, we're not going to be writing massive numbers of Bohr diagrams. These are my representation of the Bohr diagrams, if you recall. We're going to very quickly simplify it down to Lewis diagrams. They're easier to draw. And we're going to make it even simpler with something called an ionic equation. But this is a useful way to represent what's actually happening so that you can get that mental picture of what's going on, and then when we draw the easier ones, you can have an understanding on what's happening. So we'll use magnesium as our example. 12 protons, 282 is the electron configuration. Notice we're adding energy. If this is like a little chemical equation, which it kind of is, you'll notice I've got energy on the left. That means I've inputted energy. I'm putting energy into that. That energy could be electrostatic potential energy. I could use maybe something like a Tesla coil. You remember the Tesla coil? It makes all those zapping noises. That is enough energy to pull an electron right off. Whatever that energy is. You could give enough heat maybe. Can you? Yeah, if you had enough heat, you could drive an electron off. Heat energy could do it. Yep. Anyway, it doesn't matter. We input some energy. The two outer electrons come off. So on our product side, you'll notice I still have 12 protons, 2, 8, and then the electrons that were removed. I have to still keep them in the equation to keep it like balanced, because I've got to keep all the particles. I got to make sure I can account for them. But we've removed 2 electrons from the magnesium. Magnesium needs to lose 2 electrons. Energy is required. Magnesium now has 12 protons pulling on 10 electrons, giving it a +2 charge. All right? Notice it is isoelectronic to neon, which is also 2,8. But it is not neon, because neon only has 10 protons in the nucleus, and the magnesium +2 ion has 12 protons in the nucleus. So it is different. Okay? Magnesium. Mg. How many dots go around magnesium? Yeah, Caleb? 2? 1, 2. I have to add energy to this. We just saw that. The energy that we add, I've given it a title now, ionization energy. So I actually write in this, IE. So we're adding ionization energy. When that happens, these 2 electrons are removed, and we end up with an Mg that has a +2 charge. When we have a Lewis diagram of an ion, you put square brackets around the thing, and you put the charge on the outside. This is for Lewis diagrams. In a moment, I'm going to show you how to draw an ionic equation. It's even simpler, and we don't need the square brackets. And then we need our 2 electrons that go with that. Okay? So again, this symbol right here is the ionization energy. All right? And must have those guys around ions. That's a must-have for Lewis diagrams. Okay? Now that's a lot simpler than what we've done. That's good. But unfortunately, there's a third way in which we represent the formation of ions as well, and it's even simpler. We don't put the electrons. This is called an ionization equation, and it doesn't involve the electrons or the square brackets, because we're going to treat them as if they're like just chemical symbols. It's called the ionic equation. And this is really closest to what you already know as a chemical reaction, with the symbols of the elements in that thing. So this would go right along a chemical equation or a chemical reaction that you've maybe done in the past, like a balanced chemical equation. That's really what an ionic equation is. Maybe that's the best way to describe it. It's the balanced chemical equation for making ions. And again, I'm going to use magnesium as the example. So we start with Mg again. The difference is we don't put the electrons. We look at the Mg and we say to ourselves, there's 2 electrons around that thing. Notice it doesn't have a charge, which means this is a neutral atom. It is an atom of magnesium. Again, we're going to add ionization energy. That symbol is the same. This time, we're going to form a magnesium ion. No square brackets, but just a +2 as a superscript. Again, we have to draw on our knowledge of what the electron configuration is. Here with no charge, we imagine 2 electrons in the outer shell. Here with a +2, oh, it's lost those two electrons. +2 electrons. Okay, so that's the ionic equation. Yep. Without the dots and the square brackets. Yep. Let's do one more example. Actually, I would like to do one more example. If I moved back up, I should have done one more example of, see if there's space. Now you guys get excited over that. Let's just do one more example. Let's do, let's do an aluminum. Al. Let's do aluminum. We're dealing with metals here. How many electrons in the outer shell for aluminum? Yep, 3. It's in group 3, 13. We don't care about the transition metals. We don't draw them in an ionic equation, but we can visualize them. Again, we need ionization energy. Energy needs to be put in. How am I going to draw the symbol for a stable aluminum ion? What's it going to look like? How am I going to write this thing? Yep, Dylan? This is the ionic equation. Al +3. And I need 3 electrons to finish that off. Okay? All right? Now at this point, this is what your page was supposed to look like. If you don't have the page set up, if you didn't print out the page, take a complete clean page, a new page, and you're going to write these guys down, and you're going to fill in all the information. Here's what I want you to do. Hydrogen, Lewis diagram. Now the Lewis diagram I want is the Lewis diagram for the formation of the cation. These are all in group 1. So hydrogen has 1 electron. These are the Lewis diagrams. The Lewis diagrams need the dots and they need the square brackets. Plus ionization energy to produce an H square brackets plus, and I'm running out of space, plus 1 electron. You're going to do the same for all of the rest underneath. The ion equation, get rid of the electrons and the square brackets. You're not going to put them in. H plus ionization energy to get H plus 1 electron. Again, it's all squeezed in there. It's the same as what we just did. The ion charge, or also known as the oxidation state. The ion charge is the charge that's on that ion of H, which in this case is plus 1. It's the charge on the ion. Hydrogen's a special case. When hydrogen loses an electron, there's nothing it's isoelectronic to. It's just kind of empty. It's got an empty electron shell. So isoelectronic to doesn't exist for hydrogen. There's nothing that it's isoelectronic to. Now the names of the ions, I forgot to go over those, but it's not a big deal. We can easily go over them. For cations, the name of the ion is the same as the name of the element. This is simply called a hydrogen ion. So the name for positive ions are the same as the name of the atom, except you put the term ion on the back end. Now I'm going to go through anions a little quicker. They're very similar, except now we're adding electrons. Anion is negatively charged, formed by adding electrons to the valence shell. This note, as you might imagine, is very much the opposite of what we just did for the cations, right? We're adding electrons. We're talking about the nonmetals forming anions. Stable anions gain enough to fill the outer shell. Anions have full energy levels after they've gained electrons. And again, they become isoelectronic to the nearest noble gas. So something like a chlorine in group 7 here gains 1. It then has the same electron configuration as argon. So we move ahead instead of moving up and back. It's still the nearest one, right? Energy is released when atoms gain electrons. Same thing with electrons. When an electron is added to an atom, it comes in and it crashes into the atom. It literally collides with it. It gets into one of the orbits, and it causes the whole atom to vibrate. That vibration of the atom is heat energy, and that gives off heat energy to the surrounding. So incoming electrons give energy off to the surroundings, just like if an asteroid were to crash into the planet Earth, there'd be lots of energy inputted into the Earth system by the kinetic energy of that crashing asteroid. The kinetic energy of the crashing electron causes the atom to shake. It releases energy. It gives energy off. All right? This is the same type thing that we saw. Here I've got fluorine as my example, 2,7. We add an electron to it. Notice the electron is on the left because I'm adding it to it. It fills the outer orbit and gives off energy. That electron affinity is that energy that's given off. Fluorine now has 9 protons and 10 electrons, and therefore it's got a -1 charge, and it is isoelectronic to neon. We've moved ahead by 1. Let's do some Lewis symbols for some anions, and I do want you to write this one down, because eventually you'll be doing this on your page for homework. And the example I want you to do is oxygen, so I'm going to draw a nicer, larger oxygen. These are the Lewis diagrams. So do I need the dots and the square brackets? Yes. So Lewis diagrams have the dots. 1, 2, 3, 4, 5, 6. I'm hoping you can figure that out for yourself, right? 6 electrons in the outer shell. This time we are adding electrons into those empty spaces. And this time the dots around the symbol will be full, 8 full, because they didn't disappear, they were added. So now I've got to indicate that I've added 2 electrons. So for a negative ion, it's going to have 8 dots around it to be stable. I need the square brackets so I can isolate the picture from the charge, and look at, I screwed that up. See what I did there? I went to write a plus. What's the charge on this thing? Negative how many? -8? Nope. -2, because I added 2 electrons. So that's a mistake, and my eraser doesn't work, so I'm scribbling -2. Because it gained 2 electrons. The 2 negative charges that came along with this ended up being a -2 on that ion. Plus electron affinity. That's the energy that is given off. Okay? If it's something like nitrogen, it's going to gain 3, get a -3 charge. If it's carbon, it's going to gain 4, get a -4 charge. Okay? Hydrogen can also gain 1. On the sheet, when you get to it, you'll find that hydrogen is also going to be on that list. Hydrogen can gain 1 and become a negative charge. Hydrogen's a special guy. It can lose the 1 or it can gain the 1 because it only needs 2 in that outer shell to be full. The ionic equation, no dots, no brackets. I'm suggesting to do nitrogen as the example. So with the ionic equation, we're imagining the dots are there. How many electrons around a regular nitrogen atom? Using your table. 5. How many electrons does it need for the full shell? It's going to have 8. How many does it need? 3. Does that make sense? Plus 3 electrons. Another way of looking at it is on your periodic table. Use it as a grid to help. Here you are, 1, 2, 3. It's going to get me to there. What's the charge on a nitrogen ion? What's the charge on a nitrogen ion? Yep, Taylor? -3. Plus electron affinity. One thing about the name, all right? The name of a negative ion has the "ide" on the end. So this is called a nitride. Oh, look at that. Nitride ion. Put an extra something in there. It's because I'm looking at the time. When the time gets close to the end of class and I'm not done, I get a little shaky and I make mistakes. All right? It's called a nitride ion. Put an "ide" ending on the end. Don't mind that picture because we've already concluded that it is not the same as what's online. What I need you to do here, and notice how the writing doesn't move. It's kind of a pain. So I'm going to clear the writing here. Clear ink. In this one, same type thing, except this time we're starting at group 14. If you wanted, you could start with the group 17 and add 1, add 2, add 3, add 4. Okay? Again, Lewis diagram needs the dots and the square brackets. Ion equation, no dots, no square brackets. Ion charge, that's pretty obvious, the negative charge it becomes. Isoelectronic 2, we already have that. And the name of the ion gets the "ide" ending. If you don't have that sheet printed, right, you could go home and print that off in order to finish that off for homework. All right? There are a few questions that ask you to kind of summarize the charges that you found on the stable ions.